Hello, my name is Sean Giblin, and I'd like to tell you a little bit about the magnetism and superconductivity research that we do here at Cardiff. This is going to be a really brief introduction to what we do, and it just gives you a flavour of the things we're interested in and the things that we do. But I suppose when we start these discussions, we should really ask, why do we care about researching into magnetism and superconductivity? So there's a fundamental interest of just how do things behave, but we also know there's a practical application to these subjects, and perhaps it's easier to list a load of things that we associate every day with magnetism. For example, we know that speakers, in my child's earphones for example, they rely on magnets. Relays do. Superconductivity is a little bit more tricky, but actually a nice method that combines the two is the MRI scanner. So here is a picture of an MRI scanner that I've borrowed from the NHS website, and we have a magnet here, and the person goes inside the magnet, and magnetism and superconductivity are intimately related inside an MRI scanner. Now, let me explain a little bit by what I mean by this. So superconductivity, what is this? Superconductivity is the ability of a material to pass electrical current without a resistance, and it also exposes a magnetic field. And what we find is a magnetic field that you produce by a solenoid, just so by a coil of wire, is equal to the number of turns and the amount of current you can pass through. So we need to apply the biggest current we can, so we need superconductors because they don't have resistance, so they don't dissipate the heat. And these things generally operate at 4 Kelvin. This is an MRI scanner, as I said previously, but this is a picture inside the LHC, and here they use the large magnetic fields in a superconducting magnet to guide the particles around the ring. Okay, how is this related to magnetism? Well, and why do we need it in this MRI scanner? Well, a magnet you can consider simply as this so-called spin up and spin down. So it's just a bar magnet, a north and a south, where the spin minus a half and plus a half are just the two ends, north and south, of that magnetic dipole, if you like. And we find that as you increase the magnetic field, the amount of energy it takes to flip, if you imagine your field is pointing this way and your spin is pointing this way, for this spin to flip that way costs more energy because you're forcing it along one axis. And this energy is proportional to h bar is equal to hf. H is Planck's constant. F is just a frequency. What this is saying is that as the magnetic field increases, the amount of energy and the frequency at which this spin flip occurs at increases. Why do we care about that for MRI scanning? Well, this is an experimental result in the sense that the contrast of the image you're taking increases as you increase the field. So we want big fields and high frequencies. Now, in terms of magnetism, it's really interesting because magnetism is fundamentally a quantum object, but it can be viewed really quite beautifully classically, because this is essentially like a classical picture I'm trying to introduce here. And one of the things we want to understand really is that if we keep examining what we understand about magnetism, can it be used for future applications and our future understanding? So my interest in is, I really like to ask simple questions and try and understand the basics. So for me, it's still really important to ask simple questions, and you can reveal new and exciting physics we might be able to use in the future. Now, there's lots of beautiful examples of this in the media, for example. But I'm going to talk about my understanding of how I interact with magnetic moments and what they mean to me, essentially. So, why do I care what a magnetic moment is, and so what? I mean, we all know that bar magnets work and we can use them. But what I'm interested in is there a symmetry? Is there an equivalence between a magnetic moment and an electrical dipole? Well, here is my little picture of an electrical dipole, and we have a positive and negative charge that you can separate out. Now, this is important because if we can separate out electric charge, we know we can use electricity and everything that comes along with that. But magnetism, previously, the idea of magnetism from Maxwell, for example, was that if you consider a line of bar magnets, so here's a line of bar magnets, north and south, just an arrowhead, spin up, spin positive, spin a half, spin minus a half, you can see that this is just a vector field. And if you split this magnet in half, or you chop it down the middle here, you're left just with another two magnets, and you keep chopping them up, and you're always left with this magnetic dipole. You can never separate out the charges, so you can't create a so-called magnetic monopole. even though we know that there's a charge that exists at the end. So there is a magnetic charge, but every time you chop it up, you create more charges. So what you can't do is you can't create so-called magnetic charges. Now, there must be a symmetry between electricity and magnetism, and this is what I'm interested in studying at the moment, or one area that I'm interested in studying. And there was some rather beautiful work by some guys in the UK and Germany and America who thought about this a little bit more and thought to themselves, okay, right, so if I create a north and a south bar magnet and I put them on the corner of this tetrahedra, so this is this 3D triangle thing here, and these blue and these red are just north and south, or spin up and spin down, or just arrows if you want. This is a so-called magnetic dumbbell model. Here you can see that two blobs are red and two blobs are right, so you get two spins pointing in, two spins pointing out. And all they simply said was that I can describe this on the macroscopic, on the atomic level, using this Hamiltonian, which describes the interaction between the spins on a quantum mechanical level, and a dipole moment, because these things are large moments. And they said, actually, if I flip some spins, so instead of having two red ones and two blue ones, I flip it, so I've got three blue ones and one red one. Sorry, in this case here, I'm going to create this excited particle. And what they realised, which is rather beautiful, is if you flip this line of spins, so this is a line of spins, and you flip a line of spins here, so instead of being 2 in, 2 out, it's so-called 3 in, 1 out, and it goes, and you flip this trajectory along here, they realised that the energy associated with the ground state as a function of separation is directly proportional to the Coulomb energy, the magnetic Coulomb energy. So they said that if you can create this system in real life, you can create a system where these two charges, they undergo a magnetic Coulomb interaction. So this is exactly symmetrical to the electric charge. Okay, let's give ourselves a cartoon picture of this. Well, a cartoon picture of this is that essentially we can create a lot of bar magnets, we can make all these things 2 in and 2 out, and then we can flip a few, and we notice that we're going to have north and south bar magnets. So blue is south, red is north, or vice versa. It doesn't really matter. And the point they're making is that when you chop the magnet in half, you no longer have any idea how to join the two magnet pairs up. So, for example, if I join a north and south up, that is energetically equivalent to this string, or this string, or this string, or a completely different string. So the point here is that you actually have 3 magnetic charges. These are so-called magnetic monopoles. They only exist within a crystal. And so my interest in this is, well, how do you possibly measure them? Well, you've got to develop the instrumentation to do this, and you've got to make it really cold, because you've got to get rid of all the other thermal excitation. So this is just a quick introduction into what we do. So we take this spin ice material, this is the material that it's predicted to be in, and we cool it. We cool it down to 400 millikelvin, and this to 20 millikelvin. And this is a picture of a dilution fridge. And a dilution fridge, well, it just looks like a load of metal cans. But if you look on the inside of it, it's rather beautiful. And this thing allows us to cool from room temperature down to almost absolute zero. So room temperature is 273 Kelvin, so that's 273 Kelvin, this top plate here. This plate here is at 50, this plate here is at 4 Kelvin, and this is where it gets cool. This thing uses the separation of helium-3 and helium-4 to in their dilute phase. So this is a property of fermions and bosons, and we use that to essentially cool this copper plate here down to in this particular fridge can go to 10 millikelvin. And we try at Cardiff to develop instrumentation to go on these things to measure these emergent magnetic monopoles. And we've been working on this for 10 years in different places. And so there's been some beautiful work that we've done with Carly Paulson, a friend and a colleague in the CNRS in Grenoble. And we found that we can measure the magnetic conductivity as a function of magnetic fields. So as we apply a field, we pull apart these magnetic charges, and we find that we have some kind of ohmic region. This is exactly what you see in an electrical system until you get some kind of breakdown. And note this temperature range, 68 millikelvin to 600 millikelvin. So it takes a lot of effort, but it's really quite beautiful, the physics that you can get out of these systems by thinking about how you want to explore what people propose, essentially. That's what I enjoy doing. And currently what I'm working on is I take these emergent systems and I look at a single spin, and I want to look at the crossover between the classical and the quantum dynamics. And as you can see in this graph here, I take something that is semi-classical to the first approximation, and I increase the frequency, and I see basically only 4 peaks, and I'm changing the way that the spin interacts with itself almost in a quantum mechanical sense. So we're asking these really fundamental questions, and we want to understand the fundamental basics. So that's what we do at Cardiff. If you decide to come to Cardiff, you'll be exposed to all this. You'll be allowed to come and play. I mean, you can choose where to look at in our vast research portfolio, but you can come and explore any kind of area of physics that really is attractive to you. So thanks for your time, and hope to see you soon.